The final question on the study guide we see is a free response question. We have a test plane flying in a line with positive velocity. It's measured in miles per minute for t minutes after takeoff, and v, the velocity, is a differentiable function, and they give us certain values of v up here for the interval when t is between 0 and 40. So part A, we see we have to use a midpoint Riemann sum with 4 subintervals of equal length and values from the table to approximate the integral from 0 to 40 of v of t dt. So let's go ahead and do that. We want 4 subintervals of equal length. We see that we're going from 0 to 40, which means that each interval has to be 10 units, or 10 minutes long, rather, since t is measured in minutes. All right, so in every single case, we're talking about 10 minutes. Now, we want the midpoint of each of these intervals. So the midpoint of 0 and 10 is going to be 5, which means we want that value for our velocity. And then 15 leads us to a velocity of 7. 25 leaves us with a velocity of 2.4, and 35 leaves us with a velocity of 4.3. All right, so use the midpoint sum, so now we can put all of this together. Our integral from 0 to 40 of v of t dt will be approximately equal to, not equal to, but approximately equal to, hence the wavy equal sign. And then we see 10 times 9.2 plus 10 times 7 plus 10 times 2.4 plus 10 times 4.3. And we can actually stop here because we don't need to simplify. You can go ahead and simplify this and have 92 plus 70 plus 24 plus 43 and get the total distance traveled, but you can actually stop right there, and that's actually what I would recommend. So that way we don't make any arithmetic errors, even though we do have the ability to use the calculator on this problem. Okay, now we've shown the computations that lead to our answer, so that's done. Using correct units, explain the meaning of what we just found. All right, so this is important as well. We know that if we're finding the region of the area of the region below this function, that we are looking at the total distance traveled. All right, so this is the total distance, and it says use correct units. So the total distance in miles, because we are told that v is in miles per minute. So we're talking about miles here. The total distance in miles which the plane travels, or the plane traveled, whichever you prefer, during the time interval from 0 to 40. Minutes. Again, we need those units as well. Okay. Now, part B says, based on the values in the table, what is the smallest number of instances at which the acceleration of the plane could equal 0 on this open interval? Justify your answer. All right, so we're interested in the acceleration being equal to 0. We want the acceleration to be equal to 0, and we know that the acceleration is v prime. All right, so when is the derivative going to be equal to 0? Well, if we go up here, right, we see that the velocity starts at 7, it goes up to 9.2, up to 9.5, and then it drops back down to 7. Right? Do you have an idea of which theorem we're talking about here? This is our mean value theorem going into play. All right, if we were to plot these points, all right, we're at 7, we go up to 9.2, we go up to 9.5, and then we're back to 7. Right? Now, we are specifically told that v is differentiable. All right, and that's important because that means the mean value theorem is in play. So if we were to graph this function, all right, at some point during that time, because our secant line has a slope of 0, that means our tangent line must also have a slope of 0 due to the mean value theorem, which, again, kicks into play as long as the function is differentiable. Right? And there's another region as well, between 25 and 30, where in both of these cases, the velocity is 2.4 miles per minute. So from here to here, we see 7 and 7, and then here to here, we see 2.4 to 2.4. There's no other repetition of the numbers which would cause an average rate of change to be equal to 0. Because again, what we're really doing down here is we're doing f of b minus f of a over b minus a, where this is 2.4 minus 2.4 over 30 minus 25. The numerator is 0, so the fraction is 0. And if the average rate of change is 0, then the derivative will be 0. All right? So we could do this twice, over the interval from 30 to 25 and also the interval from 0 to 15. So let's go back and answer the question. What is the smallest number of instances? And the answer is 2. All right, due to the mean value theorem. And you can write MVT, that's fine. Due to the mean value theorem, and V of 0 equals V of 15 equals 7, and V of 25 equals V of 30 equals 2.4. All right, and that is enough justification to get you your points. Part C, use the data in the table above to approximate the value of the acceleration at time t equals 12.5 seconds. Show the work that leads to your conclusion. All right. Well, when t is 12.5, that's happening right there in the middle of the interval from 10 to 15. We're looking to approximate the acceleration, which we know is the velocity's derivative. So we're trying to do an average rate of change here, but we have to use 15 and 10 because those are the closest points in the time interval to 12.5. So we want v of 15 minus v of 10 over 15 minus 10. This is what a of 12.5 is approximately equal to. Now v of 15 we see at the top of the page is 7. V of 10 is 9.5. So we can leave our answer like that, and we are good to go. Again, you can simplify it with or without the calculator, but that is a good answer. With part D, we have this new function f, which is 6 plus the cosine of t over 10 plus 3 times the sine of 7t over 40. And it models the velocity of the plane. In other words, it gives us data pretty close to what we see up here. All right. And the question, again, in miles per minute over that interval. According to this model, what's the value of the integral from 0 to 40 of f of t dt indicate units of measure? So this is a calculator question. We're using that Math 9 that we did in the lesson. So if we pull out our calculator, and we're going to go into y equals, and we're going to make y1 equal to that function, 6 plus cosine x over 10 plus 3 times the sine of 7x over 40. Now this involves trigonometry, and we are in calculus class. We want to make sure that we're in radian, so we're going to hit the mode button. In doing so, we see that the function isn't, the calculator is in radian mode, which is important. And now we can go back to the main screen, and we can practice with our Math 9. So Math 9, our low bound is 0, our upper bound is 40, and our function is located in y1. So we hit the alpha, and then the trace button, and there's our y variables. So we have y1, and we're interested in that, with x is our variable that we wrote in when we wrote the equation in y1. Now we hit enter, and we get 236.6507. Remember, we have to be accurate to at least 3 decimal places. So the integral from 0 to 40 of f of t dt is equal to 236 6.65. You can write 650, 651, 6507, whatever. You have to be accurate to at least 3, and you are allowed to truncate or round. Right? And we have to indicate units of measure. So this, we know velocity is miles per minute. We just found the total distance. Distance is measured in length units, so we have just miles. 236.6507 miles.